Welcome to the Deep Dive.
Hmm.
Today we are wrestling with maybe the ultimate technical guide.
Right.
It's a massive service manual for Volvo, Penta, industrial and marine products, and our job is to pull out the knowledge that's actually, fascinating.
And this document, it's really written for professionals, for mechanics, for engineers. It assumes you already have a deep background in this stuff.
Exactly. So our mission is to look past just the basic instructions.
Yeah, we want to uncover the engineering philosophy behind it all, the intense regulatory pressures, and just the sheer digital complexity that's baked into these guidelines.
We're treating this manual almost like an artifact, a document where every single warning, every spec is incredibly high stakes.
Oh, absolutely. We're going to find safety warnings that sound like they belong in a chemistry lab.
And then we'll pivot to the microscopic level of diagnostics, like how do you detect an engine misfire just by measuring tiny changes in crankshaft rotation?
It's a stunning blend of heavy-duty mechanics and, microelectronics.
Okay, let's unpack this. I think we have to start with the biggest source of complexity, which is the regulatory side of things. These aren't just engines. They're often certified engines. For those of us more used to, say, working on cars, what does that certification actually mean? Why does it raise the stakes so much?
That's the perfect place to start. So, certification means the engine type has been rigorously inspected and approved by a relevant authority, like a government or a maritime agency.
Okay, so it's been given the official stamp.
Exactly. And when that engine leaves the factory, Volvo Penta guarantees that it conforms to that exact certified model. That word, conformity, is everything.
So the moment a technician even touches it, they're operating under this system of enforced perfection.
Precisely. That guarantee places massive, totally non-negotiable demands on any service work. The manual is absolute on this.
How so?
You must comply with the service intervals. You can only use approved, official spare parts and service kits.
So no aftermarket parts.
Zero. And crucially, any service on something vital like injection pumps or injectors, it has to be done by an authorized, certified workshop.
I'm guessing that means no creative modifications either, even if they seem minor.
Correct. The document explicitly prohibits modifying the engine. You can't change the exhaust or the air inlet ducts unless you're using a manufacturer-approved accessory.
And if you don't follow these rules,
The consequence is huge. Volvo Penta states they no longer guarantee the engine conforms to the certified model,
wow.
and they accept zero responsibility for any resulting damage or costs. You basically lose your regulatory compliance and your liability coverage in one shot.
That's the regulatory danger. Let's pivot to a physical safety warning that I found, genuinely jarring. It's about fluorocarbon rubber.
Oh, yeah. This is one of the most critical warnings in the whole manual. It's highlighted everywhere with the warning symbol.
And this stuff is common, right?
It's everywhere. O-rings, crankshaft seals, camshaft seals. The danger comes if this material gets exposed to heat above 300 degrees Celsius.
Or 572 Fahrenheit.
Right. At that temperature, it goes through a chemical change, and it forms highly corrosive hydrofluoric acid.
Hydrofluoric acid. That's not just a bad burn. That is incredibly destructive stuff.
It is profoundly dangerous. If it gets on your skin, you might not feel it for hours, but it can cause severe chemical burns that need immediate medical attention.
In breathing the fumes.
Can cause permanent, irreversible lung damage. This is why the manual mandates these handling procedures that just feel so out of place in a normal engine bay.
So what are the protocols? It sounds less like engine repair and more like a hazmat situation.
It is a hazmat situation. You can never cut these seals with a torch or burn them. That generates the poison gas.
Okay.
Technicians have to use heavy-duty PTEs, specifically chloroprene rubber gloves and goggles.
Right.
And you have to handle the removed seal, the residue, even the ash, as if it were corrosive acid.
And there was one other detail that really stood out.
The compressed air. You are never, ever to use compressed air to blow the area clean.
Why is that?
Because you risk aerosolizing that dangerous acid residue. Everything has to be sealed in a plastic bag with a warning label. It turns a simple seal replacement into a hazardous material operation.
It's amazing to think a simple rubber seal requires, chemical hazard protocols. That level of precision seems worlds away from a wrench. But the manual shows that even a simple bolt carries its own engineering rules.
That's a perfect connection. The humble bolt is the critical anchor here.
Right.
In the manual, bolts are classified with markings like 8.8 or 10.9.
And that refers to their strength class?
Exactly.
Right.
Tensile strength. A 10.9 bolt is significantly stronger than an 8.8. We're talking potentially 150,000 psi tensile strength.
So is it really true that a bolt from a hardware store, even if it looks identical, could compromise the whole engine? What's the hidden difference?
Absolutely. The difference is the metal alloy and the heat treatment. That's what defines its strength.
So you have to put them back where you found them.
The manual stresses they have to go back to their exact original locations, and if you replace one, the new one must match the strength of material for that specific application.
And if you don't,
You're guaranteeing catastrophic failure. Putting a lower-grade bolt in a high-stress area, like a cylinder head, is just asking for disaster.
and beyond the bolt itself, the manual talks about an advanced tightening method. It's not just about torque.
Yes, angle tightening. It's a two-stage process. First, you tighten to a specified torque.
Okay,
Then, you keep tightening through a predetermined angle, say an extra 90 degrees or a quarter turn.
why do that? Why not just rely on a standard torque wrench?
Because it's brilliant engineering. Standard torque readings can be skewed by friction, if the threads are dirty or dry.
Oh, okay.
The angle tightening gets around that. By turning the bolt a specific number of degrees, you ensure it's stretched to a predictable length.
And that gives you the precise clamping force.
The exact clamping force, regardless of minor friction. That uniform stretch is what prevents metal fatigue.
Speaking of things you can't reuse, the manual is very strict about lock nuts.
They have to be replaced every single time. A lock nut works because it's deformed or has a nylon insert.
And once you unscrew it,
Those locking properties are impaired or, completely gone. Reusing one seems like a small thing, but vibration could easily loosen it, and that could be catastrophic.
So moving from metal to chemistry, let's talk sealants. The manual defines two different chemical classes.
Right, two basic families. First, you have RTV, which is room temperature vulcanizing.
The stuff you can see.
Yeah, it's usually silicone-based, used with gaskets. The rule there is you have to remove all of the old RTV completely, scrape it off, clean the surface with denatured alcohol.
And the second type is much less forgiving.
Those are the anaerobic agents. These compounds only cure or harden in the absence of air.
So when they're sealed between two metal parts.
Exactly. They're used to lock threads or seal plugs or to join two solid components without a traditional gasket.
And when they harden,
They become like glass, chemically bonded and super resistant to solvents.
which means what?
It means you can't remove the old hardened stuff, not without damaging the surface of the component.
So you just leave it.
You leave it. Your job is just to clean and degrease the surface thoroughly before you apply the new compound. The new sealant just bonds to the clean metal around the old residue.
Okay, we've covered chemistry and mechanics. Now let's get into the electrical brain that manages all of this, the engine control module, or ECM.
The ECM really is the central nervous system. It's performing continuous self-diagnosis, using sensors to monitor everything.
And it communicates problems using Diagnostic Trouble Codes, or DTCs.
Right. And those codes get stored in non-volatile memory. Most of them, the minor ones, will clear themselves after maybe 100 engine starts if the fault doesn't come back.
But not all of them. There are the Never Forget codes,
Absolutely. The never forget codes are the ones related to immediate engine protection.
like low oil pressure.
Low oil pressure, super high coolant temperature, things like that. The ECM is mandated to remember those permanently, so there's a historical record of potentially damaging events.
And this digital brain is always talking across a network.
It is. It relies on two main serial buses. There's the CADIN, or Controller Area Network, which is the high-speed bus for vital data like ignition timing.
And the other one.
The J487 bus. That's mainly for accessories, displays, and for plugging in external diagnostic tools. The ECM is constantly translating between the two.
Before a technician even plugs in a tool, though, the manual always insists on one first step.
A careful visual inspection. It sounds basic, but it's so critical. Look for chafed wires, tight bends, corrosion in the connectors.
Right.
You can probably solve half of all electrical issues right there before you even grab a multimeter.
And when you do grab that multimeter, you're looking for simple things at first.
Yeah, you start with resistance measurements with the power off. Infinite resistance is an open circuit. Near 0 ohms is a short.
And when handling the components themselves, the ECM, the sensors, there's that invisible danger.
ESD, electrostatic discharge. This is a huge warning in the manual.
How sensitive are they?
The material says that less than 100 volts of static can cause permanent damage. But here's the scary part.
What's that?
A person only feels that static sap when the charge is around 4,000 volts. So you can literally destroy a critical module just by touching it and not feel a thing.
Let's look at some specific fault codes. Start with the fuel system, DTC 0087, primary fuel pressure low.
So this fault sets when the pressure drops below 20 psi for more than 3 seconds. But what's important is how the ECM controls that pressure. The fuel pump speed isn't constant.
ECM is controlling it.
Precisely, using something called pulse width modulation, or PWM.
Can you break down PWM for us? How does that work?
Sure. The ECM is essentially turning the pump on and off many, many times per second. By changing the duration of the on time, that's the pulse width, it regulates the average current.
And that controls the pump speed and the fuel pressure.
Yep. Exactly. So if you get that DTC 0087, you'll see symptoms like misfiring, rough running, or a lack of power, especially at higher RPMs.
Moving to ignition, there's the really fascinating tech behind misfire detection, the DTC 03X series. How does the ECM know which cylinder is failing?
It uses instant crank angle velocity, or ICAV. The system is monitoring tiny, rapid changes in the crankshaft's rotation speed.
So if a cylinder misfires,
That cylinder fails to contribute power, and for a split second, the crankshaft slows down. The ECM detects that tiny dip in speed and knows exactly which cylinder was responsible.
and that ties directly to a mechanical part, the reluctor wheel.
Yes, the crankshaft position sensor reads the teeth on that wheel. On a DISV engine, it's often called a 60x2 or 58x ring.
Yeah, -2 is the key, isn't it?
It's the key. The wheel has 60 positions, but 2 teeth are missing. That gap creates an absolute reference point that the ECM uses to calculate timing and detect those velocity changes.
And a misfire is considered critical for reasons beyond just performance.
Oh, absolutely. The manual stresses that misfires are catastrophic because you're dumping unburned fuel into the exhaust.
Which then burns in the wrong place.
Right. It combusts in the after-treatment system, causing temperatures high enough to permanently damage expensive parts like the catalytic converter.
Okay, finally, let's talk about the oxygen sensors.
Yep.
Specifically the wideband sensors. It's not just what they measure, but how they have to operate.
Wideband O2 sensors are incredibly complex. They use a dual sensing element with what's called a Nernst effect oxygen pump.
Okay.
And what it does is amazing. The ECM electronically balances the oxygen level inside the sensor, and that creates a tiny positive or negative current that tells it the exact air-fuel ratio.
But for that to work, it needs extreme heat.
Extreme heat. These sensors have to operate between 700 to 800 degrees Celsius. That's almost 1,500 degrees Fahrenheit.
That is incredibly hot.
It is. The Nernst cell that generates the signal only becomes electrically conductive in that narrow, extreme temperature range. That's why the sensor's internal heater circuit is so critical. If the heater fails, the sensor never gets hot enough to work, and the ECM loses its ability to control emissions.
To wrap this section, let's look at a cool marine-specific alarm. The OceanX Water Intrusion Alert.
Right. DTCs 1547 and 1548. The stern drive's oil quality sensor is basically an electrical probe that monitors the oil's conductivity and level.
So it's using electricity to check a fluid.
Exactly. The system learns the valid voltage of new oil, let's say between 1.6 and 3.0 volts. Water is more conductive than oil.
So if water gets in.
If the voltage rises by more than 1/4 of a volt, it knows there's water contamination. That's DTC 1547.
Name the other code.
If the voltage drops sharply, it means a loss of fluid volume, so you have a low oil level. That's DTC 4248. It's just an ingenious way for the ECM to use a simple electrical property to detect a serious physical problem.
What an incredible journey through a single service manual. We started with rubber seals that can literally turn into acid.
Right.
Then we had to make sure we were using a bolt with 150,000 psi tensile strength. And we ended up diagnosing engine faults by measuring the rotation of a crankshaft using missing teeth on a wheel.
The modern mechanics toolkit has completely changed. It's not just wrenches anymore. It's digital multimeters, it's chemistry, it's software code.
That integration of all those disciplines is really the big takeaway, isn't it?
It is. Every single specification in this manual is critical to maintaining the certified performance and the safety of the entire system.
Every little detail matters.
Every detail, whether it's the specific chemical for a sealant or the 5-volt reference signal for a pressure sensor, every measurement is designed to keep this incredibly complex machine running within razor-thin parameters.
So what does this all mean for you? Well, consider the level of detail that goes into calculating the expected manifold absolute pressure based on engine RPM. The manual defines exact target pressures across different RPM bands.
Right.
What else in our modern lives operates under such a specific, hidden, performance-driven digital map? That merging of physical mechanics with regulatory software is what drives every complex machine today. It makes the service manual the ultimate guide to a world that's built on invisible, completely non-negotiable data points.